So another application for the law of natural growth is in radioactive dating. If you can imagine, you have the sample of something that was an organic compound, something that was living, and when for any living compound there's carbon. We're made up of carbon, and we have a certain amount of different isotopes of carbon that weighs a different amount. And in living tissue, the amount of carbon-14, the ratio of normal carbon or carbon-12 to carbon-14 is fairly constant as long as we're living. As soon as we die, that ratio changes. The carbon-14 decays, and it has a half-life of 5,700 years. That means after 5,700 years, only half of the carbon-14 that was originally present is present. So if scientists are able to take a sample of something that was living and measure the ratio of carbon to carbon-14, we can then use this information about half-life to figure out how old the sample was when it died, or how long ago it was when it was died, not how old it was, how long ago it was when it was died. So what we're saying is that the amount of carbon-14, the rate at which the carbon-14 changes, is proportional to the amount of carbon-14 present. So we've got the law of natural growth happening. In this case, it's natural decay, actually. And the solution to this is this equation, which I have proved to you in the first slide in this lesson. So we need to use this equation if we've got some questions around radioactive dating. So let's say we have a sample, and scientists have measured that it's got 90% of its carbon-14 left. They know what it should be for a living object, and they can measure it now, and there's only 90% left. How long ago did it die? Or how long ago did that sample die? So what we want to first start with is find out what K is, and we're going to use the half-life to do that. So the amount of sample we have left after 5,700 years is half. So we have half of the original amount left after 5,700 years. So I've just plugged in 5,700 years for the T, and I know that the amount that I'm left with is half of C0. I'm going to divide the initial amount out because it's the same on both sides, and I end up with an equation that looks like this. Now I'm going to take the log of both sides, the natural log, and natural log of 1/2 is 1 minus log 2, and log 1 is 0, so you'll often see the natural log of 1/2 written as negative log 2. Oops, I forgot my E there. Let me rewrite that. Natural log, when I took the log of both sides, I forgot my E, so the natural log of 5,700K. Now these two are inverses of each other, so they'll cancel, and you just end up with 5,700K. And that means I'm allowed to find out what my K is, which is negative log 2 over 5,700. Now I'm going to use my constant here and plug it into my equation. So I know that my amount of carbon-14 is the initial amount times E, and this is negative log 2 all divided by 5,700 times T. So if I know that there's 90% left now, let's find out how long it took to do that. So I've got 90% of my sample left, so 90% of C0. The C0 I'm going to cancel again. And it's a bit messy here. Now I'm going to take the log of both sides, So I'm going to take the log of 0.90 and I'm going to take the log of the right side. When I take the log of the right side, it will cancel the e because those are inverse operations, and I'll just be left with log 2 over 5700 times t. Now I need to just get t all by itself, so I'm going to multiply by 5700 and divide by negative log 2. And there's my time, and if I work that out, it's about 866 years. So a couple of things to notice here. Does it make sense that the k is negative here? Yes, it does. And it does because it's a decay problem. So for any time we've got decay problems, we want to make sure that k is negative. And we're going to be doing several more types of natural growth and decay problems in the slides to come.